All right, welcome back. Today we're going to continue our discussion of L'Hopital's rule. So remember, L'Hopital's rule is a way to, it's like a shortcut rule for limits, but it involves derivatives. Therefore, we're talking about it now that we have derivatives under our belt. Um, and the last video, we did all limits as we were approaching a finite value. In this video, we're going to look at limits as we're approaching as x is increasing without bounds. We're approaching infinity. So 6 examples here. Let's just hop right in and see what happens. Remember, we have to double check before we apply L'Hopital's rule to make sure that the function is in the correct form. It has to be a certain type of indeterminate form. And also remember that notice all these are quotients. L'Hopital's rule only works for quotients. Or perhaps functions that can be rewritten in quotient form. All right, so A, you have the limits as x goes to infinity. We have x minus 8x squared over 12x squared plus 5x. Maybe I'll solve this using L'Hopital's rule, and then I'll solve it using the method we used back in chapter 1, just to show you how we get the same answer. So first of all, notice that if we take the limit of the numerator and denominator individually, the numerator is going off to negative infinity because we have that negative quadratic term. That's going to dominate the numerator and go to negative infinity, and the top and the bottom is all positive, so it's going off to positive infinity. But those are both polynomials. So a polynomial is always going to have a limit at infinity of either plus or minus infinity. So negative infinity over infinity, that was one of the proper forms for the application of L'Hopital's rule. So what does L'Hopital's rule say to do? It says you can take the derivative of the numerator and denominator individually. So no quotient rule, just take the derivatives individually. So that's going to be 1 minus 16x. And then the denominator will be what? 24x plus 5. And if the limit of the new function, if it exists, it's going to be equal to the limit of the old function. Okay? But here's the problem. Notice that's still in negative infinity over infinity form. If you look at the limit of the top and bottom individually, they're still going off to negative infinity and positive infinity, respectively. But here's the thing: you can apply L'Hopital's rule again. We saw that in one example in the previous video. So apply L'Hopital's rule again. So the derivative of the numerator is negative 16. The derivative of the denominator is 24. And now we have a constant function. And you can always find a limit of a constant function. It doesn't matter what we're approaching, whether we're approaching infinity or negative infinity or a finite value, the limit of a constant function is always that constant function, which of course reduces to what? Negative, you divide by 8, negative 2/3. Okay. Now, how might we have solved this back in chapter 1? In chapter 1, we would have said this. Divide the numerator and denominator by x raised to the greatest power on the denominator. So notice the highest power of x in the denominator is 2. So what we would have done in chapter 1 would be to divide the numerator and denominator by x squared. In other words, multiply the top and the bottom by 1 over x squared. So equals the limit as x goes to infinity. What that's going to do for us is basically divide each individual term. There's 4 terms. Divide them all by x squared. So we get x over x squared. Minus 8x squared over x squared. And then we have 12x squared over 12. Nope, not over 12x squared, just over x. Oh, what did I do that for? It's 8x squared over x squared and 12x squared over x squared. Sorry about that. Over x squared, and then what? 5 over x squared. Which then, if we simplify each of those individual quotients, that gives us what? 1 over x minus 8, and then 12 plus 5 over x squared. Okay, now and here's the inside. Now I'm gonna gloss over a couple individual steps here, but we've been doing limits for a while, so this should be fine. Basically, we have a property that says you can take the limit of a quotient, you can take the limit of the top and bottom, the numerator and denominator individually, provided the limit of the denominator is not 0. And it's not going to be. Okay. Then we have a property that says, well, if you have the limit of the sum or difference of values, you can take those limits individually. So what that allows us to do here is take the limit of these 4 quotients individually. So what do we get? Well, we get the limit of 1 over x as x goes to infinity is 0. The limit of a constant function is that constant function. The limit of a constant function, again, is 12. Of a constant function, 12 is 12. And then the limit of that bottom right hand, again, why is the bottom right hand and the top left 0? Because in both those cases, the numerator is constant, but the denominator is growing. So both of those, the top left and the bottom right quotients tend to 0. And notice what we get. We get negative 8 over 12, which kind of looks different, but if you simplify it, you get 2/3. Exact same answer. Which one's harder? I mean, I'd probably say the chapter 1 method probably is a little harder. L'Hopital's rule is probably a little bit easier, but they both get you the same answer. Okay? So you can use either way, unless there's a specific way. Of course, maybe there's a specific way requested for a test. But in general, if you just need to find the limit, do whatever feels best to you. Whatever method you prefer. Okay, let's look at example. Let's do D actually. I want to show D because I want to look at D 2 ways to solve it, or maybe just one way to solve it. Let's see. All right, so the function or the limit in D is the limit as x goes to infinity. 3x over radical 2x squared plus 1. Now, of course, we should double check to make sure we can even talk about L'Hopital's rule. Notice though, if we take the numerator, the limit of the numerator and denominator individually, well, the top is going off to infinity. If x increases, the top just increases. And the same thing for the bottom. Now the bottom, well, let's see. The bottom, you're taking 2 times the value squared, then taking the square, adding 1, then taking the square root. So it's got more complicated stuff going on, but it's still going off to infinity. So this is infinity over infinity form. We're good to go there. Okay, so we can apply L'Hopital's rule, which says differentiate the numerator and denominator individually. So the derivative of the numerator, of course, is just 3. Now the denominator, that's a composite function, so let's do that off to the side. First of all, we rewrite the square root as 2x squared plus 1 to the 1/2 power instead of square root. Now, of course, composite, so we have an outside and inside function. The outside function's x to the 1/2, the inside function's 2x squared plus 1. And the chain rule says you take the derivative of the outside function, so 1/2 times something to the negative 1/2 power. Then we evaluate that derivative at the inside function, 2x squared plus 1. And then we multiply by the derivative of the inside function, which is 4x. And then if we simplify, okay, there's a 4x on top and a 2 on the bottom. That's going to leave me with a 2x on the top. And then that negative exponent right there means we kick that term to the denominator, and we have a negative 1/2 power. But remember, we have a positive 1/2 power at that point. But remember, a 1/2 power, that's a radical. So we could say plus 1, that's the square root. And now this is the derivative of the denominator. So we have to put that right here. So radical 2x squared plus 1. Now that looks kind of weird. And so it's a compound fraction. We have to remedy that compound fraction. Okay, so we have 3 divided by a fraction. And how do you divide by a fraction? You flip the divisor and multiply. So that's going to give us on the top radical 2x squared plus 1. Actually, 2x squared plus 1, 3 of them. divided by 2x. And now look what L'Hopital's rule did for us. It didn't do anything for us because we differentiated the top and the bottom, and we got a function that still has a radical in it, except now, the denominator is a polynomial, but the numerator is a radical function. So it didn't really help us out at all. And that's going to happen sometimes. There's some times where L'Hopital's rule is sure you can apply it. You can apply it until the cows come home, but you're just going to like flip back and forth between different forms of a limit, and none of them are really good. So I put that there on purpose because to show you that L'Hopital's rule is not always advantageous. So how would we solve this? Well, let's go back and now we'll do the chapter 1 way. Okay, now, there's actually a couple different ways where you could solve this. I don't really have a super preference. Basically, you can factor, you can multiply, or you can or use the composite property of limits. I tend, I guess, to use the kind of like a similar method to example A, where we divide by an appropriate value, and that appropriate value is well, I guess we'll determine that in just a sec. So limit as x goes to infinity. Actually, let's do that up here. Then we can rewrite on the next line. So on example A, when I did like the chapter 1 way, we divided by the highest power of x in the denominator. So basically, I want to divide by x squared, but that x squared's under a radical. So basically, I need to divide like this. Oh, let me. That's way too big. Come on, OneNote, erase. All right, there we go. I want to divide, so 1 over square root of x squared. Or actually, I should write it like this. Actually, I was right the first time. That looks better. 1 over square root of x. Why? Well, because I can't just divide by the square root of x because, if I can't just divide by x squared, if I do that, the x squared can't go under the radical. But if I multiply by radical 1 over x squared, and again, this goes over the entire thing, then it's proper to move that under the square root sign. Okay, but of course I can't multiply or divide the denominator without doing the same thing to the numerator. So I have to do the same thing up here. 1 over x squared under a radical. So now I've multiplied by 1. Okay. Now here is what that does for us. On the denominator, I can move that x squared under each term. So that's 2x squared over x squared plus 1 over x squared using the distributive property. But what about the numerator? So I have 3x, but okay, let's think about this off to the side. 1 over x squared. If I wanted to simplify that, how could I do that? Well, we could take the square root of the numerator and denominator individually. Of course, the square root of 1 is 1. And now here's where we have to be careful. Because the square root of x squared technically is equal to the absolute value of x. Because in general, you don't know, because if you square a term and then take the square root, you could have started with a negative or a positive value. So that's why we do the absolute value of x. However, we are taking the limit as x goes to infinity. So we know x is positive. So we don't have to worry about the whole absolute value business. We know that we are talking about positive values. So we know that reduces just to 1 over x. So this, on the top, the radical 1 over x squared is equal to 1 over x because we know we're working with positive numbers. So I can multiply by 1 over x or just divide by x. Okay, and now that gives me what? That gives me a Just if I simplify this, the limit as x goes to infinity. That gives me just a 3 on the top. And on the denominator, I get what? 2x squared over x squared is 2. And then I can just have 1 over x squared. That doesn't simplify right now. And now I can take the limit. Again, technically at this step, we're actually using several limit properties. We're taking the limit of the numerator and denominator individually. And then we're actually using the composition rule so we can take the limit underneath the square root. And then we're using the sum difference rule to take the limit of, of those two terms individually. But once we do that, we notice that we have the limit of a constant is 2. And then the limit of this function, well, the numerator of that quotient is constant. Denominator is growing, so it has to be equal to 0. So what we get is 3 over the square root of 2. And that is how we would solve that limit using chapter 1 techniques. Okay? And again, L'Hopital's rule doesn't work. I'm tempted to show you another way to solve D, but I'll leave it there. I'll leave it there. Okay. Since the purpose of this video was, of course, to evaluate limits, use L'Hopital's rule if we can. Now, of course, we couldn't use L'Hopital's rule, or we could use L'Hopital's rule there, but it was not advantageous. So let's just stick to that one method. And now let's go to B, I guess. B is a lot easier, actually. Okay, we have the limit as x goes to infinity. I'm pretty sure we don't have any problems with L'Hopital's rule. Okay, let's think about this. We need to make sure it's in the correct form. X squared, clearly, if we're going to look at the numerator and denominator individually, the denominator is clearly going off to infinity. And natural log, remember the function natural log looks like this. Oh, not like that, sorry. Looks like, come on. Erase. Or maybe not. OneNote doesn't, okay, there we go. OneNote didn't want to erase. Natural log looks like this. So of course it goes off to infinity. So both the top and the bottom are going off to infinity. So it is infinity over infinity form. So we can certainly use L'Hopital's rule. Okay? L'Hopital's rule then says to take the limits of the numerator and denominator individually. So the derivative, sorry, I said that wrong. It says to take not the limits individually, the derivatives individually. So the derivative of natural log is 1 over x. The derivative of x squared is 2x. Now that's a compound fraction, so let's remedy the compound fraction. And okay, we have 1 over x divided by 2x. So think about 2x as a fraction also. And that means if we're dividing by a fraction, we flip the divisor and multiply, which gives us 1 over x times 2x. Which, okay, that's 1 over 2x squared. Now clearly, if the numerator is a constant, but the denominator is growing pretty fast, 2x squared gets really big really fast, but the numerator is constant, that means the fraction is just going to 0. So we get a limit of 0. Again, anytime you have a situation where the numerator is constant, but the denominator is increasing or maybe decreasing towards infinity or increasing towards positive infinity, you have to get an overall solution of 0. Because the top is static, but the bottom is either growing to infinity or negative infinity. Okay, so L'Hopital's rule was a big help there. About C. All right, we have the limit as x goes to infinity. Natural log x plus 1 over log base 2 of x. Okay, this is kind of a weird one. I don't think we ever had anything this weird with two different logs with different bases in chapter 1. But let's see, let's see if L'Hopital's rule will help us out. First of all, notice this is in indeterminate form because the top is going off to infinity and the bottom is. Why? Again, think about the graphs of these logarithms. Basically, log base 2 looks like that, and it's going off to infinity steadily up and to the right. Natural log of x plus 1, well, okay, that's been translated to the left 1 unit, but otherwise it basically has the same graph. It just has an asymptote over here instead of the origin. And they're both going off to infinity. So it's clearly in infinity over infinity form. So we can apply L'Hopital's rule, and we're going to then differentiate the numerator and denominator individually. So let's see. Well, the top is composite. Okay, chain rule time. So we have, let's do it up the side. The derivative of natural log x plus 1. Okay, the outside function is natural log x. The inside function is x plus 1. Okay, so chain rule says you take the derivative of the outside function, you get 1 over x. But you evaluate it at the inside function, so x plus 1. Then multiply by the derivative of the inside function, and the derivative of x plus 1 is 1. So there's our derivative, times 1, but you can just leave it as 1 over x plus 1. So that's the derivative of the numerator. Now the derivative of the denominator, it's not composite, but it's non-base e. So recall that the derivative of a non-base e logarithm is 1 over x times natural log of the base, so natural log of 2. All right, compound fraction like we've seen several times now. So let's remedy the compound fraction. Limit as x goes to infinity. We have a fraction divided by a fraction. So that's going to give us 1 over x plus 1. And now let's see what happens. We flip the divisor and multiply. So that's going to give us, I messed up my plus sign. 1 over x plus 1. And then we flip the divisor and multiply. So what does that do for us? Oh, I didn't do that right. Of course, that x plus 1 does go on the bottom. But we flip and multiply. That gives us x times natural log of 2 on the numerator. Okay, it's still not abundantly clear what's going on there. So let's see if we can apply L'Hopital's rule again. Notice the top is linear and the bottom is linear. So they're both just lines. Like the top has it's basically a line with a slope of natural log 2. The bottom is a line with a slope of 1. They're both just lines, kind of like going like that. Okay, so they're both going off to infinity. But it is important that we do have to check that, of course, because if not, then we can't apply L'Hopital's rule. But this is the correct form. Infinity over infinity form, or one of the correct forms. Okay, so we can apply L'Hopital's rule. Take the derivative again of the individually of the top and the bottom. So what's the derivative of the top? Notice it's x times natural log of 2. Natural log of 2 is just a constant, so we can apply the constant multiple rule and say, okay, what's the derivative of x? 1, and then multiply by natural log 2. What's the derivative of the denominator? X plus 1. Just 1. And cool. So we have a constant function. So the limit of a constant function, regardless of what you're approaching, is simply that constant function. So there is our answer. Okay, natural log of 2, unexpected. If you had given me, given this to me, and said what's the limit, I would have had no idea that it was natural log of 2 off the top of my head. But L'Hopital's rule gives us the answer right away. Okay, right away. Well, not right away. Close to right away though. We just have to differentiate a couple times, and then of course check to make sure we're doing things properly. Okay. All right, let's look at, we did D already, so let's look at example E. Oh, Example E. All right, we have the limits. Okay, we have an exponential function. As x goes to infinity, we have e to the 2x over x cubed. Okay. Is it in the correct form? Yeah, it is. Yeah, it is, because, okay, exponential clearly going off to infinity. X cubed, again, if you cube a big positive number, you get an even bigger positive number. This is going off to infinity pretty quickly on the top and the bottom. All right, so we differentiate the top and the bottom individually. All right, the top requires a little chain rule, right? E to the 2x, it's a composite. Outside is e to the x, inside is 2x. Okay, so chain rule says you take the derivative of the outside function, you get e to the x. Easy enough. Step 2 of the chain rule, evaluate at the inside function, so plug in a 2x instead. Third step of the chain rule, multiply by the derivative of the inside function. There you go. I'll put the 2 out front though. 2e to the 2x. All right. Derivative of the denominator. Oh, that's super easy. Power rule. 3x squared. Okay. Well, still not super clear what's going on, but notice we're still in indeterminate form. The top and the bottom are both still going off to infinity. So let's see if we can apply L'Hopital's rule again. Limit as x goes to infinity. All right, notice on the numerator, we have 2 times our original numerator. In other words, we can apply the constant multiple rule and factor a 2 out of the derivative. And then we already know what the derivative of e to the 2x is. It's 2 e to the 2x. Derivative of the denominator, 6x. All right, okay, so now we have what? 4e to the 2x on the top and 6x on the denominator. Okay, they're both still going off to infinity individually. So this is still infinity over infinity form. So let's see about applying L'Hopital's rule again. Limit as x goes to infinity. Okay, of course the denominator is 6. That's the easy derivative. Now notice the top is 2 times 2, which is 4, a constant, times e to the 2x, times a variable function. But we know the derivative of e to the 2x is just this. So 2e to the 2x. And now I think it should be obvious what the answer is, because the denominator is a constant. The top is not a constant. It's a exponential, which is going off to infinity. So here, now we don't have L'Hopital's rule form because the top is infinity, but the bottom is a constant. But that should tell you what our answer is. If the top is going off to infinity, but we're just dividing by a constant, that means the whole overall quotient is going to infinity. Okay, because imagine the numerator is getting bigger, 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 a million, a 10 million, a billion, a trillion, and we're dividing by 6. The dividing by 6 is not doing anything when you're approaching infinity. So our answer is infinity. Okay? So that was the first one where we had an infinite limit after using L'Hopital's rule. All right, what about the last one? What is f? Example f. Let's see here. We have the limit as x goes to infinity. 3x plus cosine x over x. All right. Can we apply L'Hopital's rule is the first question. Let's think about this. 3x plus cosine x. That's kind of like a weird function that kind of goes like this. Kind of like that. It's like a combination of cosine, so it's periodic. But it combines the linear part, so it's kind of like a linear function kind of going crazy like that. So yeah, it's going to infinity. So yeah, the numerator is going to infinity. And of course, you know, x just looks like that. Well, except it's supposed to pass through the origin. So yeah, it's going to infinity also. So yeah, this is infinity over infinity form. Okay, so we're good to apply L'Hopital's rule. So we differentiate the numerator and denominator individually, and we get what? 3 minus sine x if we differentiate the two terms in the numerator individually and the denominator individually. Okay, well, that just leaves us with, without a fraction, it leaves us with this. And it's okay, we can't apply L'Hopital's rule again because we don't have a quotient. So let's think about what's going on there. Like, what does that graph look like? I mean, we should be able to think about the graph here and know what the answer is. So we're looking at basically the end behavior. The limit as x goes to infinity. What does 3 minus sine look like? Okay, well, we have minus sine, so that's the sine flipped upside down. So instead of like going kind of like this, oh, that's terrible. Instead of going kind of like, come on, you can do it, erase. Maybe not. Sometimes OneNote likes to lag a little bit. There we go. So instead of, sine going, I'll be more careful this time, kind of like this, a negative sign flips it. Okay, so here's my terrible rendition of sine x. Here, let's do negative sine x. If you just flip it, it goes kind of like this. So there's my terrible rendition of negative sine x. Okay, if you add 3, it just takes everything up 3 units. Okay, so I'll roughly draw that with green. So imagine the red translated up 3 units. Basically, goes like this. Okay, I know that's terrible, and I missed the y axis. I missed the y-intercept. So that, anyway, very rough sketch. But think about it this way. This is just going forever, up and down, up and down, up and down. Are we approaching any specific y value? Like a limit at infinity means as x gets really, really big, you get 10 million, x is 10 million, 20 million, 100 million, a billion, a trillion. Those y values are approaching a single value, consistent value. Would sine approach a consistent value? Okay. It's bouncing back and forth between, the range originally is between -1 and 1. But if we translated it, up 3 units, it would be between -1 plus 3 and 1 plus 3. So 2 and 4. It would be between 2 and 4. Okay. So yeah, it's going to be bouncing back and forth. That tells us that the limit does not exist. Okay. The limit as x goes to infinity does not exist because we're not approaching anything specific. We're just constantly bouncing back and forth, back and forth. Y values are going back and forth, back and forth. They're not approaching any one specific y value. So the limit does not exist. So there we have it. L'Hopital's rule, we could apply it, and basically that helped us maybe more easily see the solution, because to be honest with you, I have no idea what that graph looks like. But I can figure out what this graph looks like just using what I know from trig class of how to translate functions. I guess I reflected the sine function over the x-axis, and then I translated it up 3 units. So L'Hopital's rule allowed me to get the function in a more easily recognizable form. Okay, and of course, yeah, that's it. So L'Hopital's rule for us. In this video, we found that sometimes L'Hopital's rule is helpful, other times it's not. But of course, we always have to check for indeterminate form, either 0 over 0, like the last video, or infinity over infinity, or some combination of negative infinities and infinities. I think if you have any questions, always feel free to reach out. I'll catch you in the next video.